This problem is about a power series and the domain of power series, what's known as the interval of convergence. Okay, so first let us start. The power series is, the given power series is sigma of minus 1 to the n over n natural log of n x to the n, and because we have n and natural log, we cannot take 1 nor 0 nor 2. I'm sorry, 2. So we cannot take 1 and 0. So we can take 2 from 2 to infinity. So we need to find the domain, and remember the interval of convergence, or the domain, is given by the radius of convergence. So the key here is to find first, okay, find the radius of convergence. So we need the coefficients an. So we have an equals minus 1 to the n over n natural log of n. And here I'm going to use the, for r, I'm going to use the ratio formula. Okay, so here we have an plus 1 equals minus 1 to the n plus 1 over n plus 1 natural log of n plus 1. So now absolute value of an plus 1 over an is, so we can remove the minus 1 to the n, and we have a fraction over a fraction, so it's going to be the top fraction times the inverse of the bottom fraction. So we will find 1 over n plus 1 natural log n plus 1 times n ln of n over 1. So this gives me that an plus 1 over an equal n over n plus 1 and natural log of n over n plus 1. So if we use the this here, we can use infinity over infinity for the limit, and we will find by Hopital rule 1 over 1, so it's 1. And the same goes for this one. We can use again Hopital rule, and we'll find 1 over n plus 1 for the derivatives. And we'll find that the limit is 1. So each term has limit equal to 1. So by Hopital rule or by other means, we'll find that the limit of an plus 1 over an is equal to 1 when n goes to infinity. So the radius of convergence r is equal to 1 over limit of absolute value of an plus 1 over an when n goes to infinity. And also some people, I like to use this formula, but some people, they like to use the inverse of the sequence, which is exactly the same. Okay? And the limit will be 1 over 1 equals 1. So we know now, next, we need to find out what happened to the series when x is equal to r equals to 1. So we have sigma, the original series, minus 1 to the n over n ln of n times 1 to the power n from n equals 2 to infinity, which is the series minus 1 to the n over n ln of n from n equals 2 to infinity. And here, so since we're looking at the domain of convergence or the interval of convergence, there is no need for us to waste time in looking at absolute convergence when x equals to r or not. And here I can see that the series is alternating, and therefore I can look at 1 over n natural log of n and see what happened to this sequence. It's very easy because n times log of n is increasing and it goes to infinity. Therefore, this sequence is decreasing and it goes to 0 as n goes to infinity. So it goes down to 0. And now we can use AST because it's alternating. The alternating series test tells us that this series is indeed convergent. Next, we look at x equal minus r minus 1. So in this case, we have the series becomes, this is the coefficients, minus 1 to the n, and this becomes sigma of 1 over n, natural log of n equal 2 to infinity. So for this one, we can use the integral test, because this is a Bertrand series, so this is Bertrand series. But in any case, we're going to use the integral test by taking f of x equals 1 over x, natural log of x, for x greater than 2. We know that f of x is decreasing and positive, so f of x is decreasing because xn of x is increasing, so when you take the inverse it becomes decreasing, but you can take the derivative as well, is decreasing and positive. So we can use the integral test. So we know from the integral test, so the integral test tells us that the integral from 2 to plus infinity of f of x dx is convergent if and only if the series f of n from 2 to infinity is convergent. So one is convergent, the other one is convergent, and vice versa. Otherwise, if one is divergent, the other one is divergent. So here we go ahead for the improper integral, 1 over n x natural log of x dx. So that's the limit using the properties of the improper integral, or the definition, from 2 to a, 1 over x ln of x dx. And here we need to find an antiderivative of 1 over x ln of x, and we're going to take u equals ln of x, a substitution, and we will find that by taking substitution u equal ln of x, that this is equal to ln of x plus c. Therefore, the integral from 2 to plus infinity 1 over x ln of x dx, that is a limit when a goes to infinity of ln of x between 2 and a, which gives me limit when a goes to plus infinity of ln of a minus ln of 2. So again, a goes to infinity, so this one will give me ln of plus infinity infinity, ln of plus infinity infinity, therefore it's infinity minus a number, so this is equal to plus infinity. So this improper integral here is divergent, which gives me what? That the series 1 over n ln of n from 2 to infinity is divergent by the integral test. So this implies that that the domain or the interval of convergence is equal to minus 1 is out and 1 is in, or if you prefer, minus 1 1, 1 is in, 1 is out. Next, we look at the series, which is just shift. So we shift the series to get horizontal shift to get the new series, which is minus 1 to the n over n ln of n x plus 1 to the power n. So here basically the interval is shifted. Interval of convergence is going to be the set of x plus 1 between minus 1 and less than 1, which is equal to, we bring minus 1 to the other side, minus 2 x 0. Okay? Or if you prefer, the rotation minus 2 and 0, 0 is x.